topic to last time. So for the people who don't know me, obviously I'm Chris, and I'm kind of a bit of an all-round open sourcey geek, really. I've got a fair long history of both being a Java developer and Postgres DBA, as well as kind of DevOps. And I have a open source monitoring project that I previously spoke about here. And I also occasionally dabble with building hardware. And obviously a big OpenSUSE user. So, you know, now that CentOS is gone, you should move to OpenSUSE. So what we're going to talk about today is Postgres, which, as some of you may know, is the world's most advanced open source object relational database. So the project itself has got a fairly interesting history in that a lot of the core code and the concepts date all the way back to 1982. 1982. And the Postgres project actually was started by a guy called Michael Stonebaker, who was at UC Berkeley, and is probably best known for Ingress. Postgres is named because it's post-Ingress, for those that didn't know. And that mainly stayed a project inside Berkeley until about 1995 and 96, where what we now call the Postgres project or PostgreSQL came along. So originally Postgres didn't actually have any SQL support, and a bunch of people decided to pick up Postgres in 1996 and add SQL support to it. And that's the project we now have today as Postgres SQL. And to clarify the naming a little bit, the official name is PostgreSQL, but everybody just calls it Postgres, and I shall probably just use Postgres for the rest of this talk. However, it's not called Postgre, it's Postgres or PostgreSQL. And in the database world, Postgres is really quite highly regarded for its kind of focus on reliability and data integrity. And I've been working with Postgres now for 14, 15 years, and I've never really been bitten. And a lot of the way it approaches stuff and its adherence to the SQL specification, for example, is around making sure that your data has always got a level of data integrity. And you can't do weird things like cast a string to a date like can in MySQL, and with some very strange conversions that can go on. And there's a really huge wide array of features, and there's a bit of a focus on these features all being robust and correct. And often, I think Postgres has one of the highest adherences to the SQL spec out of most of the databases, especially open source ones. And again, it's also got nice focus on performance and scalability, and Postgres can run really on your average desktop or your small little kind of WordPress type site, all the way up to multi-terabyte data warehouses. And I've run Postgres at those different scales. So I've run Postgres on hundreds of servers in one place, and I've run Postgres with a 10 terabyte database in another place. But I think one of the key things for me about Postgres that makes it very special is how extensible and flexible it is. As a natural database engine, pretty much everything can be plugged and changed through extensions. And this has kind of given Postgres a fairly long history of innovation. And there's a number of things in the kind of database, especially the open source database world, where Postgres has done things first and actually really kind of pushed things forward and competed with very different database platforms. And that's something I'm going to talk about going through this talk. So this talk is really kind of a bit of a general tour de force around Postgres. So we're going to have a look at installing it, getting it up and running, and then some of the kind of cool, neat things we can do with it. So we won't be going into too much detail on a lot of topics, but if there's certain things that people do want to ask questions about, please just ask them as we go along. You can either put them in the chat or speak if you want to. And the other thing to mention is that it was announced this week that Postgres has won the Database Engine's Database of the Year for 2020, which now makes it the third time that Postgres has won this award. And I believe that's more than any other database. So with that, let's get started with how do we go about installing Postgres? So obviously, we're all Linux users, given that this is a Linux user group. And the really simple, trivial answer here is that your distribution almost certainly has Postgres in its repository, in its packages. So there is also on the main Postgres website a whole bunch of official packages for a range of different distributions, such as Debian, SUSE, off the top of my head. And these are provided by what's called PGDG, which is the Postgres Global Development Group. So obviously, using OpenSUSE as my distribution of choice, installing Postgres really is a case of these two commands: zipper install Postgres, systemctl start Postgres. So most distributions will split Postgres into the client libraries as well as the server libraries. And there's usually as well an additional package called contrib, which contains a number of additional extensions that get shipped with the core product. And since I think Postgres 11, there is also now an additional optional dependency which enables just-in-time compilation of queries via LLVM. So that's often, so the final package we have here is Postgres 13 LLVM JIT, which adds that support in. And again, that's kind of designed to be an optional add-on so you can not install it if you don't have LLVM, for example. So now we've got Postgres set up, we kind of really want to probably connect to it. Now, Postgres by default is fairly conservative, won't allow a lot of remote connections. So what we need to do is use the PSQL command line tool. So PSQL is Postgres's CLI SQL client. And to connect, we need to kind of run that command as the Postgres user on the server. So that will drop us into a SQL shell and as the Postgres super user. So that gives us full administration access to Postgres. Now, obviously, a lot of people prefer to use graphical clients. So there is something called pgadmin 4, which is the kind of de facto graphical client these days. There's also a lot of people who are not necessarily so keen on pgadmin 4. And there's a number of alternatives, OmniDB being my preferred option. And then there's other third-party proprietary products as well, such as dbeaver and Navicat, all the work. And to be honest, these days, Postgres is so widely used, there's so much support from different tools to connect to it. And one interesting thing to note about Postgres, especially if you're more used to MySQL, is that a server hosts multiple databases. And this often gets termed a database cluster. So a running instance of Postgres will have a directory called the data directory. And inside there will be a number of folders that will represent the different databases. So an important thing about this is databases are completely isolated from each other, so that you can't query across databases. This kind of, if you come from the MySQL world, where actually what MySQL calls a database is more of what is normally called a schema, you can still do schemas inside Postgres databases, and they're used for namespacing different entities and objects within inside your database, if you so wish. And when we first connect, we will find that there's a default database called Postgres that exists. There's also another couple of small databases called templates, which are used when you create a new database. However, really, you shouldn't really use any of these three databases. And the first thing we should do is create a user and a database. So as I said before, right, we run the PSQL command line tool and we connect to Postgres, and we're going to create a role. So obviously do this to SQL, create role. And then so PSQL has a number of built-in commands, all of which start with a backslash. So \password is a built-in command that allows you to set the password for a user And this is the best way to change a password for a user, because it doesn't mean that the actual password you enter enters any log files anywhere. So once we created a role, we can go and create a database. So create database owned by, and we have a database we can now use. And we could use the command \c to connect that database now if we wanted. Now, probably one of the most asked for questions on Postgres is, how the hell do I quit PSQL? Which has lots of many funny ways to do it, such as opening another terminal and typing pkill PSQL. But in fact, the command you want is \q for quit. So now we've done the very basics of connecting to Postgres. Let's talk a little bit about the Postgres kind of configuration. So Postgres has two main configuration files. We've got postgres.conf and pg_hba.conf. And these are per database cluster, so they're per instance of the Postgres server you have. And typically these files reside within the data directory. So on most distros by default, that's var lib pgsql. Some distributions, Debian specifically, and Ubuntu tend to move these files into etc. But the kind of official place for them is inside the data directory. Now, the postgres.conf file is the main configuration file, and this has a huge number of options about the Postgres server. And a lot of these default options are quite conservative. And then the pghba file is what controls and configures how remote hosts can connect to Postgres and how they must authenticate. So HBA stands for host-based access. And in this kind of main purpose is purely about controlling network clients. And Postgres has quite a number of pluggable different authentication schemes you can use, and this file controls all of that. The handy thing with this particular file is you don't need to restart the whole Postgres server to change this file. You just need to send the server a SIG-HUB, which is usually, say, systemctl reload. There's a number of commands, there's a number of options inside the main postgres.conf file that you can also just do a reload rather than a restart, but there's another whole number of options that require a full restart. Now, I think I've briefly mentioned this, but the kind of Postgres configuration by default is extremely conservative. And this kind of goes back really to my point about Postgres is quite regarded for kind of reliability and safety. And by default, remote access isn't enabled. And if people have seen the stories about Mongo databases being publicly available on the internet, this is just something that doesn't happen with Postgres by default. So, but obviously this isn't useful for a lot of people. So the first thing you kind of really need to go and do once you've installed Postgres is enable remote access. And there's basically one line inside the configuration file you need to change for this, which is listen_address. And it will be commented out by default. And if you remove the comment and set it to star, it will listen on all interfaces. You can obviously specify different IP addresses you want to bind on, that kind of thing. And then kind of associated with this, there's also a configuration option, which is controlling the maximum number of connections to Postgres, called max connections. And that's a hard limit on the number of clients you can have connected. Postgres has a very traditional model, we would call, in terms of how it handles clients, in that it's a full-on forking server. So in terms of the processes you will see in Linux with Postgres running, there will be the main kind of post master process, which is the kind of control process that will accept connections, and then every connection that's accepted and authenticated, it will fork a process to run that connection and to provide.
So Chris, a quick question about that. Does it have connection pooling at all?
No. So this is a point where, so ultimately Postgres kind of connection is fairly so creating a connection in Postgres is kind of considered quite heavyweight, in obviously it's got a fork connection. There's also a whole bunch of other things that has to happen for concurrency control. So there's snapshots that need to be taken internally of the concurrency tracking. So really, you don't really want clients to be connecting and disconnecting often. But Postgres itself doesn't do any connection pooling. However, there are associated projects, such as probably the best known one is called PG Bouncer, which runs as a connection pooling and has some very advanced features. Yeah, exactly. Enter PG Bouncer. So, I mean, this is one of the kind of dichotomies of Postgres at times. There's a lot of discussion inside the community about how much should Postgres have in core versus like how much of the Unix philosophy should we have that these kind of very specific scenarios are to be done by external kind of systems. And there's other parts in like the Postgres stack where that's very much true. So yes, if you're running with a very high number of clients, then you want some kind of connection pooler, and probably PG Bouncer is the way to go. I think there are a couple of other ones that have popped up the last couple of years. And there's obviously some other ancillary configuration things you want to probably pay attention to, such as logging. By default, there's not very much logging that goes on, and it's not very useful. But again, the config file's very handy in being well annotated. And if you have any intention of taking backups and doing replication, then out of the box, it's usually worth setting what's called WAL senders to at least greater than 1, and as well as the WAL level to a slightly higher level. And obviously, in terms of remote access, you need to go through the PGHBA file and kind of configure what remote users you want to allow to connect. So that's a case of specifying which databases they connect to. It's very powerful, and also which authentication schemes they use. At the end of the talk, I can show some config files and stuff, but otherwise it'll get complicated to keep switching between the windows we're sharing. So when I was kind of chatting to some friends about this talk, a few of them mentioned that it would be nice to kind of cover some of the little gotchas that a lot of people overlook when they're setting up Postgres. And performance is a really huge topic and can't really cover a lot of it, but there's a kind of a number of key things that goes back to Postgres's default configuration being very conservative. And it's very conservative about the amount of memory it will use by default. Now, obviously, if you're running a dedicated database server, having 256 megabytes of RAM for the entire space of holding database pages that can be modified is a bit small for most people for those kind of situations. So the biggest kind of tunable parameter you need to look at first is what's called shared buffers. So this configures a shared memory pool that's used by all of the back-end connection processes to access both database pages and to modify them. So any write in Postgres goes through this pool of shared memory. So the rule of thumb these days is that you set that to about 25% of your server's RAM. So if you've got 64 gig of RAM in your server, then it's something like 16 gigabytes. Next, the kind of main thing you want to start tuning is around WAL and how much is retained before you do something called a checkpoint. So I think it's important now to explain what the concept of WAL is. So WAL stands for the write-ahead log. So the write-ahead log is you might know of a transaction log from other systems. Pretty much every kind of database system has the same kind of concept, that any change you make to the data stored, you first write into the write-ahead log. Now, this is all done to meet the durability criteria of ACID compliance. So this is about ensuring that data written is really written and never kind of lost, is durably written. But this also then has a kind of trade-off between there's a time where data is written to the WAL files. It's not yet written to its actual real location. And the client, you haven't told the client yet that the transaction has been committed. So at the point that the database server tells the client the transaction is committed, what is guaranteed to have happened is that that data has been written to the physical storage inside the WAL. So basically data changes are written to the WAL, what's called an Fsync will happen that will ensure that that WAL is on physical disk, and then the client is happy and its data is safe. Now, obviously, we have that kind of detachment between, we have this log that's been going along, and then we've got the data pages that will get written down in the background. Now, what we don't want is if the server crashes at this point and we restart, we then have to go and replay all of those WAL files because we can't guarantee what was or what wasn't written to actual disk. So there's a kind of time window effectively where the size of your WAL will increase the amount of time you spend in kind of recovery if you need to restart the server. So these are configured by two parameters inside the config file called min WAL size and max WAL size. And this basically kind of configures and constrains that window. And that's kind of really tuned based on how much writing you're expecting to do on the database. So if you're a very heavy kind of OLTP high-level transaction system, that's probably going to be quite a high number in probably say 8 gigabytes, something like that. If you're kind of a much kind of lower throughput system, that's probably going to be a lot lower. And that also plays into how fast data is being written in the background. And at the end of the day, is your database server to get good performance, you kind of want to try and keep your IO consistent so that you don't have huge spikes of writing to disk heavily that causes issues for, say, clients that are just trying to read data. Now, there's another parameter that a lot of people quite often try to crank up, which is called work mem. And this is a particularly dangerous parameter if you go and set too high, because this parameter is allocated per connection, and it's also allocated multiple times per connection based on what the queries are doing. So if you work mem by default, I think is 4 megabytes. If you go and set that to 256 megabytes and you haven't got a terabyte of RAM, you're going to run out of memory very quickly, and your system really won't be making much use of its resources. Now, obviously, these days as well, a lot of people are running on SSDs. And one of the great things with SSDs is they are basically as fast to access a random block of data as they are to access a block of data sequentially. Postgres has a number of settings which controls how it will execute and optimize a query based on these kind of parameters. So if you're running on SSDs, there's a parameter called random page cost that you want to set to basically 1, which means a random page is about as fast as a sequential page. And then the other thing that I've seen, sadly, people turn off, which is something you should never ever do, is called Fsync. So as I already explained, Fsync is extremely pivotal in ensuring that your data doesn't disappear. And don't ever turn it off because you will lose data. Whilst it might be attractive, especially if you're running on slower hard drives, to get the performance gain, it's not a good idea. You're better off turning Synchronous commit off instead. And there's a number of handy websites these days, but pgtune is quite a nice one. You select a couple of parameters and it'll generate these key settings for you. So in terms of more kind of performance things, as I mentioned, use SSDs. There's really not any reason these days not to be. The speed of NVMe especially is just staggering. File systems, not really too much of a problem here. Most of the modern file systems are extremely fine for running Postgres. XFS has always been the one I've got best performance out of myself, but ext4 and Btrfs these days are just as good. Don't run Postgres on NFS though. And then at the kernel level, there's a bunch of things you should really be tuning, especially for a dedicated server. So on the dedicated server, you really want to be turning memory overcommitting off. So there's a setting in the kernel called VM overcommit. And that effectively allows malloc to allocate more address space than you have physical RAM for. On a database server where we basically want to try and prevent systems crashing more than anything else, it's well worth effectively constraining how far the kernel itself can over allocate memory. And the first time I kind of paid attention to this parameter was when a colleague executed a query that did a self join on a table, and tried to eat through several hundreds of terabytes of temporary disk space and memory to execute this query because they forgot to put an equal sign in. So these are kind of useful things to set up, especially if you have a dedicated server where actually stability is more important than other things. And the other thing it's useful doing often is turning swap off, and tuning the page cast dirty writing. So obviously Postgres makes use of buffered IO to write to disk, which goes through Linux page cache. So what we want to do is try and make sure that that's configured to have consistent writing, kind of consistent IO. So we want to just be constantly writing to disk slowly in the background rather than doing it in big spikes. And there's a number of parameters inside the kernel kind of sys settings that will set this up. So dirty cache write back ratio is the number one. And the other really important thing to do if you are looking at performance issues is just benchmark stuff. So Postgres comes with a benchmarking tool out of the box called pgbench. And that's super useful for just capturing a baseline of your system, and then as you change parameters, seeing how things improve, and comparing with other people as well. There's quite a lot of published benchmarks around these days. And then also, at the end of the day, Postgres will never be faster than the physical disks and file system it's running on. So things like Bonnie, Sysbench, FIO are very good for kind of that low-level testing as well. Now, another real thing that catches people out, especially until it got changed, was Postgres's numbering, Postgres's versioning scheme, and the complexity around upgrades. So the last 4 releases, 5 releases ago, we changed the numbering scheme. So the current release is Postgres 13, the previous release is Postgres 12, the previous release of that was 11, and then 10. The previous release before 10 was 9.6. The previous release to 9.6 was 9.5. And if you go back further than that, it all gets a bit random in places where the first digit was bumped for certain reasons occasionally, and it was all done on a bit of a whim, really. And it was extremely confusing to a lot of people. So it's very important to realize that Postgres 9.5 and Postgres 9.6 are different major versions of Postgres. And that going from 9.5 to 9.6 is a major upgrade, and it can't be done by just install the packages and restart. So minor changes are, for example, 13.1 to 13.2 or Postgres 9.5.1 to 9.5.2. And they are simple. They're just install and restart. So Postgres 9.5 will go out of support next year, well, this year. And Postgres 9.6 will leave support 2022. So two more years and we won't have to put up with this crazy numbering scheme. So the Postgres data directory that we've already talked about, it's important to remember that that is not compatible between major releases. So you can't start a Postgres 13 server with a data directory that was written by Postgres 12. It's also, you can't change that between different CPU architectures. So if you had Postgres running on an ARM machine and Postgres running on an x86 machine, you can't interchange those data directories. So this has been one of the reasons that upgrades has been historically a bit of a problem in Postgres. However, a few years ago now, probably about 5 years at least, that we have a tool now called PG Upgrade, which solves a lot of these problems. So that will allow you to convert the data directory from one version of Postgres to the other version of Postgres. And to do this, you basically have to install both versions of Postgres on the same server, and then kind of run this command, which will, but it's important to note that this command is offline, so you can't do an online upgrade of Postgres using kind of this approach. However, because of the way it works with hard links and stuff like that, it's actually extremely fast. So you can upgrade a multi-terabyte database in a matter of seconds with some then work to do once you start back up. So that kind of covers some of the more low-level kind of sysadmin side of Postgres, really. And what I kind of wanted to talk about next was kind of how we kind of configure Postgres as a topology. So how do we kind of cluster Postgres? How do we have high availability? How do we do sharding if we need to? And this is an area where certain other databases are actually pretty good at having a lot of this out of the box and pretending it kind of solves all your problems. Whereas Postgres, it goes back to that kind of Unix philosophy thing to an extent. It has the tools inside it to be able to do this, but it relies on other products and tools to actually kind of do that properly as a full kind of end-to-end system and solution. So these building blocks are effectively replication. So replication allows us to take data from one Postgres server and send it to another Postgres server. And this was first introduced about 10 years ago now, I think, in Postgres 9, and it's what's called streaming replication. So this relies on the write-ahead log that we've already talked about. So the write-ahead log contains every change that's going on inside your database. Now, what streaming replication does is push that to your replica server, and your replica server just replays that log as it would do if it was in what's called recovery mode. So we can take two servers as long as they start from the same kind of base image of each other, which we can take through, say, a file level backup with, say, PG backup. Forget what's called that shift of med. And we can then configure these two servers through the main configuration file for the replica to connect to the primary and to stream down those logs and to stay in sync in an asynchronous fashion. So it's important to realize that this, again, is only compatible between databases that are the same major version. So you can only replicate Postgres 13 to Postgres 13. You can't replicate Postgres 12 to Postgres 13. And again, this is because it's effectively sending the raw binary data over, and that's being replayed on the replica server. Now, the replica servers can run in what's called hot standby mode, so they can actually accept queries and process queries whilst they're kind of running in this continuously replaying the data coming in from the primary server. So this then allows you to be able to utilize those replicas in a read-only fashion. Now, it's important to remember that this is asynchronous out of the box. So there is a lag between when you write on the primary server and that data being available on the replica server. And that's very much dependent on your network bandwidth, your disk bandwidth, your CPUs, and how much data you're writing. So if you're writing lots of data very quickly, that lag is likely to be quite high in potentially the hours region. If, on the other hand, you're writing a relatively small amount compared to kind of the variables of network, disk, and CPU, your lag's probably a matter of milliseconds. But we do have another mode of streaming replication, which is synchronous streaming replication. Now, this is useful in those situations where you really need that kind of durability guarantee that you don't ever lose a transaction. And synchronous replication will effectively block the client from committing that transaction until that data has been written to potentially all the servers you have in your kind of synchronous cluster. So it also supports a mode called Quorum Commit. So as long as the majority of the servers specified have written that transaction to all of their disks. So in other words, the primary has it and say at least one other replica has it. Then that transaction is considered committed from the viewpoint of the client. And you can optionally enable this on a transaction by transaction basis, but it's probably a fairly rare use case. But so, for example, if you're running a bank, you're probably using using synchronous replication. But obviously that does come with trade-offs because there is a speed of light involved between data getting from the primary server to the replica. So your kind of latency in this kind of mode is going to be substantially worse than in your kind of asynchronous mode. And then we now have, since Postgres 10, a third type of replication, which is called logical replication. And this is I would call it a scalpel versus the sledgehammer of string replication. So it's much more targeted. It allows you to replicate on a table by table basis. It even lets you replicate into different systems using different formats. You can pull the data out of Postgres in any kind of way you want to a large extent. And this is all based around, again, obviously it all goes back to the WAL stream at the end of the day, but logical replication is all built on decoding that WAL. So the WAL data is things like, this row has been changed and a whole bunch of decoding is done to that binary record to turn it back into effectively the SQL statement that was executed. It also takes care of all the initial synchronization for you. So when you create publications and subscriptions, when a subscriber connects to the publisher, it will first off sync down the entire copy of that table, and then it will start receiving all the changes. And the really cool thing with this is you can do it between different major versions of Postgres. So we can actually use this to do live database upgrades if we need, although it's quite a lot of work for some, depending on your kind of database setup. But it also lets you kind of do fun things like you can do multi-master two-way replication. You can go and replicate into other systems, for example, say Kafka or Pulsar, which could then go and push that data off. You can pull the data out as just JSON if you want. So it gives you a huge amount of kind of possibilities and things you can do. And obviously it's a fair bit newer than the streaming replication, and it's only been around for the last 3 or 4 releases. So with those building blocks, we then kind of get into probably the way that most people want to run kind of high availability Postgres, which is one primary server, one or more replica servers, and a load balancer in the middle that controls where your clients talk to. So as I mentioned, Postgres has the building blocks for this, but it doesn't do it out of the box. And specifically what it doesn't do out of the box is knowing if a node is dead or alive and who should be the new primary. So if you imagine a situation where the primary database server has failed, you need to promote one of the replicas to be the new primary. Now that requires you first off choosing the correct one to promote, and then repointing the other replica at the new primary. So that's not so trivial. So there's a whole bunch of external tools that help us do this. And probably the best one really around is something called Patroni, which uses an etc.d cluster to kind of manage that kind of cluster state. There's another option called, I think, PG Auto Failover, which I think is from Microsoft. And often these tools will make use of something like HA Proxy or PG Bouncer to direct the traffic between nodes from your clients. There is also some options built into the official Postgres clients to support connecting to a list of servers and picking the most appropriate one. Now, quite often, lots of developers, especially people who are used to, say, Mongo, want to talk about sharding because usually they think this will solve all of their problems. And in my experience, sharding is an extremely double-edged sword. It's usually for very niche use cases, and most people don't need it. Most people don't like to realize that they are not like the scale of Google or Amazon or Facebook or Twitter. Most people are probably okay getting away with one box, and often, especially these days with the speed and scale of modern hardware, just scale up a box. Get a bigger box is always your first approach. And ultimately, at the end of the day, distributing data across multiple servers is extremely complicated and extremely difficult. And this is where something called CAP theorem comes in. So consistency, availability, and tolerance to network partitions. And effectively, you can choose 2 of those 3, but not all 3 of them. And there's been a number of kind of highly modified versions of Postgres that have tried to build effectively a fully distributed ACID compliant Postgres. One being PostgreSQL, which probably got the furthest. I think it's currently a bit of a mothballed project, sadly. But that is probably the full-on, if we really wanted, multi-node distributed Postgres. But there's a whole bunch of other approaches that various people have used depending on your kind of situation, what you're working on. And one of the oldest approaches to kind of this, how do we shard multi-node Postgres, was written by Skype probably almost 15 years ago now, called PL Proxy. It's a very specific way of doing things that a lot of people aren't keen on, where effectively you write procedural functions to access your data, and then they proxy across databases. A more newer way has been features introduced through foreign data wrappers. So foreign data wrappers allow Postgres to go and access data that resides in foreign systems. And through that, you can actually build some sharded setups, especially now with the table partitioning. And there's other approaches with logical replication you can do, and there's specifically some proprietary projects called BDR, bidirectional replication, which especially if you're doing geographic multi-master setups, that's the kind of thing you're probably worth looking at. And then another big one is called Citus, which is now owned by Microsoft and I think available in Azure Cloud as well as a kind of proprietary extension, which allows you to do kind of sharded Postgres with some trade-offs and limitations. So with kind of that being the end of all of kind of like the low-level infrastructure stuff, I kind of really want to talk about how Postgres has kind of innovated, and especially how it has countered a lot of the movement or fad towards NoSQL that happened over the last kind of five years or so. One of the really cool things that Postgres kind of added that really kind of, to my mind, elevated its position a bit and actually directly made Postgres compete against NoSQL, especially databases like MongoDB, was Postgres's work to support JSON. So a lot of NoSQL databases are all designed around document databases where you're storing schemaless data. A lot of people call this unstructured, which isn't strictly true because it is structured data. JSON is highly structured. You just don't define the schema up front, usually because you're lazy. Pretty much most systems always have a schema, and it's usually easier to define it and manage it than it is to try and work it out in 3 years' time, especially when you need to go and try and query backwards compatibility. So Postgres added data types which were called JSON originally, which was just a text wrapper for validated JSON. But then came along something called JSON-B, which is what's really very impressive, which is a binary representation of JSON in Postgres. So Postgres has an extremely rich pluggable data type system. And anybody in any extension can write a data type and you can then use it. So JSON-B is a data type. So we can have a JSON-B as a column, and that then allows us to store a full JSON document into a single column in a single row. And this can also be completely fully index accelerated. So as a lot of people used to joke at the time, we now have MongoDB in a column and we're faster. So how do we go about using this? So now it's time for kind of the SQL section of my talk. So JSONB is quite simple. Again, all we need to do is declare a column of type JSONB. And then because we want to be able to index accelerate this, we're going to create an index. And actually that index uses a method called gin. And that's not just because I like drinking gin. But gin is a different index type in Postgres. So Postgres supports more than just B-tree indexes. So gin is used for kind of lossy data where there can be multiple keys that point to rows. And we can then have a whole bunch of operators that work on this JSON data. So we can go and access a single field of that JSON record. So in our column, we have a JSON object. And there's a field in that object called command. And this funny operator arrow with a double head will go and extract that value and convert it to text. So the result of that query will then be that one value from that field inside the column. And then we can do the same, but we can do this for, say, a JSON array. Now, what would be really cool, obviously, is can we go and search on that kind of same data? So I want to search and find a document that has a field called name with the value test1. Now, this might seem like a valid way to write that. However, it's extremely slow. I mean, it still executes in 3 seconds on my machine with a table of 18 million rows. However, that's not really as fast as we could be. If we use a different operator, which is this magic at arrow thing, which is what's called, is basically a contains operator. So what we're saying here is, does my JSON document contain a field with this of name with the value test A? And that is fully index accelerated, and on my machine, again with the same data set, takes 3 milliseconds. So that's 1,000 times plus faster to execute that query. But the kind of, we can go even further. So we can go even further with this.
Hey, Chris, Zach had a question about
Sure.
would just a select splat from that field work as well? Work as expected, I should say.
Select star. So, like, if you're trying to export a table, would that work?
Yeah.
For my personal work, that's what I'm doing a lot.
Yeah. Select star. There's a lot of people that say you should list all the column names, but also that's a lot of effort, right? So sometimes it's worth listing the column names, but it depends on how sensitive your application is. If you change the structure of that table, for example, things like that, or if, say, columns get moved around, but select stars, it's perfectly fine. There are a few caveats, but they're quite advanced. If you're using column level permission grants, then select star does cause problems, but a lot of people don't touch that. So the other cool thing we can do with kind of JSON is convert rows to JSON, and obviously aggregate as well, multiple rows into an array. So for example, we can dump a whole table as a single JSON tree. So that will return an array of objects where every row is a JSON object. We can also build specific objects. So that would construct a very straightforward JSON object. So this is all extremely powerful. And this can also then be really useful if, say, for example, you want to pull a row with then a nested list of kind of child objects or child records that relate to that. So traditionally, like an ORM would have to execute this with what's called the n+1 problem, whereby we do one query and then we have to go into a second query for every row returned. Whereas using this kind of approach to structure all your kind of relational data into kind of an object type structure as JSON, you can kind of reduce some of these network overheads and latency problems by basically just getting everything as you want it. And I think, to be honest, this is kind of stuff that it would be quite nice if people started using it more. And I'm in the process of expanding it and using it to, yeah, XMLDB. That was fun. And there is a huge amount of parallel here. It's except JSON's cool these days and XML isn't. And there's parts of the SQL 2020 spec, for example, 2018 spec, I think, which is SQL JSON, which Postgres are in the process of implementing. It's kind of Postgres got in this weird position of they were like the first relational database to add all this support. And then they went and wrote the spec, and the spec's completely incompatible with what Postgres did. So in the process of Postgres now implementing the spec, they're having to change a lot of their underlying things that work here. And so the actual SQL spec JSON supports, we have things like JSON paths, so you can do full level path queries into structures. So you can go and find, for example, you want to find all records where the second element of an array called parameters is C or something like that. So this is all extremely powerful. Again, all index accelerated, so works extremely quick, extremely well. And like the other kind of NoSQL product I've seen get very popular over the last few years has been Elasticsearch. And in fact, like the first real big project I did with Postgres was building a search engine. And back at the time, text search in Postgres was not in core Postgres. This was an extension. This was with Postgres, I think 8.1. And Postgres getting full text search support and the work that went in to make that happen has been quite fundamental in a lot of things, because all of that work implemented effectively completely pluggable index system in Postgres. So I mentioned that Postgres doesn't just have B trees. We actually also have index types called gist, gin. We have Brin as well these days, space partitioned gist. You know, there's a huge range of indexes, and there's a group of people that just have various different cool new index ways of doing things as extensions. So for example, rum and vodka were some of the ones that came out of the original people behind all those pluggable indexes. And full text search leveraged that to start with. So full text search, you're taking text and you're breaking that text down into the basic lexemes. So the basic lexical structure of a language, a written language. And then you're matching against those kind of lexemes. So effectively this is all how the text search of like Google, etc. works, is you break down your document into all of the different pieces, and then you effectively count all those pieces, also keep track of their position. So Postgres can do all of this. It's all got ways to kind of rank how much your query matches those documents. And it provides what's called stemming and snowballing. So stemming allows you to truncate words down so that plurals get stemmed down to just the root word. Snowballing does kind of similar kind of changes. There's also thesauruses you can apply. Supports multiple languages. So this is really powerful. And the really cool thing about all of this being inside your kind of main database is you can join it up with other things. So there's nothing stopping you combining JSON and full text search. So to actually use full text search in Postgres, we use another specialized data type called TS vector, which is a text search vector. So that basically computes all of the different lexemes in a bit of text and tracks them. And again, we use our magical GIN index to be able to search that super fast. And so we can put some data in here. So I'm just creating TS vectors here from some text I have in a different table. And then we can actually query it. And the querying is super powerful. You know, we can do things like has this word and this word, has this word or that word. You can do prefix matching. You can do this word must be within 2 words of this other word. You can do kind of phrase searching. So it's extremely powerful. And all you need to do is use these kind of magic data types and a magic operator. So in terms of, again, like the extensibility of Postgres, there's a project called Postgis, which is a complete geographic information system for Postgres. So this adds in geographic and geometry data types, and a huge number of functions to work with these data types, and also provides a number of external tools for mainly loading and processing data. So this is highly compatible and comparable to Esri's ArcSDE or Oracle Spatial. And it's probably one of the most well-regarded, especially open source GIS systems these days. And actually getting quite a lot of traction, even in the people who make maps, such as like Ordnance Survey and things like that. And what's notable about this is it's an extension. It's probably the biggest kind of third-party extension to Postgres. And this means you have to install it as a separate library. So what we need to go and do here is install another package. So in OpenSUSE land, that's called Postgres version -Postgis. And that will install the shared library that you can load into Postgres. And once we have that in Postgres, we can then just create that extension, and then we are free to use Postgis inside our database. So create extension Postgis. That will then install Postgis into your database. And you have to do this per database in Postgres. And then we can make use of it. So here's a query that's using a magical function called st_d within. So this is doing a distance-based geographic search. So in this particular example, we're looking for a physical point that's within a 2 kilometer radius of another point. So, and then there's a whole bunch of functions that lets us to do all these kind of queries. And again, all of these queries are then index accelerated. So super fast to kind of do all this geographic processing. And what's really cool by all of this being in your database is you can combine geographic search with text search. So an example of this is the search engine I wrote was for a kind of government organization here in the UK. And our search engine, you could write, find me a library within this distance of me. And because of the way we had a bit of metadata on our web pages, so our web search engine was then able to go and say that, okay, this page has a geographic relationship, and we can then work out that this term matches text-wise, and it's kind of close to you, so it's the most appropriate for you, which was some very powerful stuff that you just really can't do if all of these data stores are different and independent from each other. And the last kind of topic I wanted to talk about is SQL in 2021 and how SQL is a lot more than most people's conception of SQL, which really dates back to kind of SQL 92. A lot of people are still only really familiar with in my experience. So a little very cool thing that a lot of people don't really know about and use is the ability to use what's called common table expressions to break down big queries into much more readable chunks. So in this particular case, we have a number of tables that we union together, And rather than keep repeating that kind of stanza, we can just create effectively an alias for that query. So with checks, which is the name, and then we can effectively use that name as a table in the rest of our query. And underneath, this isn't actually materializing anything like that. It's just syntactic sugar that the planner can still do all of its optimizations. And in fact, now we can explicitly say to materialize or not materialize depending on performance benefits of either approach, depending on what you're doing. But this then leads on to a very powerful form of common table expressions, which is called recursive common table expressions. So this actually allows you to effectively do graph processing in SQL inside your database, inside Postgres. So in this particular example, I have a table of groups where groups can have a parent relationship to another group. So we effectively have a cyclic graph, and we can query that and build that whole thing just with a recursive SQL query. So here the actual database will go and keep querying based on the data until it's built that full graph and returned it. So this is very interesting if you do play with any kind of graph type stuff. And if you were to do this through some more traditional ORMs, you would have an extremely slow query. So another cool little nice feature that's best supported in Postgres, especially if you're doing lots of reporting type stuff, is filter. So this allows us to provide a predicate around a aggregation function. So in this particular example, right, I have a table of state, and I want to count different kind of specific values. And this is really simple to do with filter. You can also do it with case statements, but this is nice and straightforward and very clean syntax. And a feature that I'm very fond of that's actually got much more common in most of the relational database engines over the last few years, but I think Postgres does have the best support for them, is what's called window functions. So these are very cool aggregate functions that allow us to slide over the result set as we process things. And this allows us to do things such as go and find the previous row. So this is an example from some kind of smart metering system where we have a table of counter readings from an energy meter. And we want to calculate the energy consumption for that day. And this window functions make this super easy to do because we just go and find the previous record using lag in a window and then do that simple difference. And we can get even more complicated by specifying how we partition these windows. So this particular example, we're going to take that same kind of computed energy consumption and then also put a column of that consumption grouped on a week by week basis. And what we're going to do here is just sum up that data in a week bucket. And we can even go even further and actually do ranges based on physical rows. And in this instance, we effectively can compute a moving average. So if we want a 2-day moving average looking backwards, this is all really nice and simple to do with window functions and extremely powerful. And kind of, I think this is going to be my last thing, is Postgres is so kind of flexible that you can even write your own aggregate functions. So we can write functions, and you can write functions in a huge number of different languages in Postgres. And then because it has this completely pluggable type system and kind of aggregation system, we can actually then define the aggregate that uses that function we wrote. So thank you very much for listening. I hope I didn't bore you too much. And is there any questions or anything we want to talk about?
Yeah, I think, shoot. Michael, did he answer your question or not? I didn't know if I caught it or not.
I don't know if you did or did not answer my question.
Want to ask it
If you want
again?
to ask your question again, then we'll talk about it.
Okay, so I think you said it's the GIN index is a magic index. So that looks like to
Yeah,
me
kind
that
of.
it doesn't do like multi-column index. So if you select on like the query that
So
has
it's not
more
quite a
than one,
multi-column index. So obviously Postgres supports multi-column indexes anyway. Multi-column indexes are usually more about like if you have different columns that all correlate to each other, then you then store it effectively as a chain inside a B tree or something. GIN is more about so if you think about the kind of full text case, you're splitting that data point into actually hundreds or thousands of different individual data points. But a lot of those data points are also going to be shared with other rows. So then GIN is kind of optimized for that situation where you'll have a key inside the index that will point to potentially hundreds of rows. So it's very handy for kind of like low cardinality type columns or a lot of these kind of more exotic data types. So GIN often gets used with kind of the full text search side, the Json support side. There's some use of that kind of stuff inside some of the geographic stuff, but there's also other index types that get used. But what's really cool is that kind of like full text search work that happened about 15 odd years ago probably introduced this whole kind of approach to having pluggable indexes. And Postgres has got a huge number of different index types. And if you have, a very specific problem domain and use case, you can actually write your own data types and you write your own index if you really wanted to.
okay, thank you.
So Chris, when you do the text search, is it all based on just flat text, or is formats like if you had let's say you had a huge directory full of Microsoft Word or some kind of other binary format that people use for document handling or PDFs, for instance? Is it able to deal with
So
those
yes
formats?
and no. So internally, it does have a kind of a whole parsing system, but it only really supports kind of plain text stuff out of the box. So you can like index HTML, for example, but you can't really index, say, those more difficult formats.
Well, I was curious because back in the days where Microsoft had proprietary formats and didn't use the open docs, or at least pretend they did, we had to use third party. We couldn't, Oracle's own systems depended on third party vendors to provide that feature.
Yeah, so for the aforementioned search engine I wrote, I actually implemented document search support on it. We used OpenOffice, and there's a whole bunch of weird APIs into OpenOffice, and you can run it in a server mode. And so basically we had, our indexing subsystem that was going and crawling our web content and our like shared network drives would throw that document into OpenOffice.
Oh, okay. I thought you
And then
pass the
basically
XML
pull all the text out and then put that into Postgres. And yeah, to be honest, it was something I wish we never did, because OpenOffice itself used to crash on a probably minute by minute basis.
Yep.
Memory leak like nothing. PDFs, on the other hand, were quite straightforward. But again, so our indexer just pulled all the text out of those documents and just put the text into Postgres. And then the kind of text search in parsing system inside Postgres is good at dealing with the kind of plain text, but not really with binaries. In theory, there's nothing stopping people writing all of that support inside Postgres, but I don't think there's anybody interested in doing it. So that's probably the answer.
So how advanced is the query language when you do? When my background is, when I last did this, it was all XML, and it did an okay job if you had basic queries. But once you have advanced queries that says, let's say this element needs to follow another element, sequentially, or as a parent-child relationship, or something else, it started showing this was meant for relational databases, not for unstructured data.
So in terms of like the JSON support, The JSON path stuff is actually very powerful. Like, so you can specify and look through quite deep nested data structures. You can apply like ternary operators, multiple predicates, that kind of stuff. It's surprisingly powerful. How much you want to do that is a different question. And obviously you can still combine multiple SQL predicates in its own right. So if you wanted to combine the results of multiple path checks and things like that.
Let me give you an example of the kind of queries that I always fought with, right? So I dealt with data with a lot of positional data, right? So you would have a contact, what was it we were looking at? And then other elements would say, what was the data associated with that? And maybe some more characteristics. And what I would have to do is to see what contacts are of this type could I find within a certain location. And these are all data that may not be a parent-child relationship, right? They may all be in the same structure. So you have to be able to query and say, inside of this block of this major key, I need to make sure that this value is that, and then I need another value within that block returned.
Yeah.
And typically, I found that very, very hard to do with the unstructured data options.
Yeah. I mean, yeah. So again, the path support would let you look in that kind of way, and obviously there's, it's how your predicates are different to what you extract out. So if you just want to return the whole thing, or if you want to return a portion of that thing, or you want to return a specific field, it's completely decoupled. How trivial it would be is a very different question, because to be honest, it's probably just a complicated use case, full stop, right? I suspect it's not that easy to do in other systems, full stop.
Outside the database, I had no problems doing that. But okay, I was just curious to see how advanced this indexing was today, and because quite frankly,
if you ever use like JQ command line,
I use
believe
JQ quite a lot. Yes, JQ.
Similar.
Yeah, JQ can do it. Yep.
So if you can do it in JQ, then I believe you should be able to do it with the JSON path support.
Okay, well that's pretty cool. Okay, thanks.
That's really tough.
My JQ foo though is kind of fairly limited to maybe pulling out and checking a value of an array or something like that. So yeah, I mean, if you've got any particular examples, I'd be interested.
Yeah, JQ's syntax can be a bit daunting, at least to me.
Yeah. And there was another one I've used a fair bit with Ansible, was it JMS path, which again
Yes.
was
Yeah. Anybody else have any other questions? Before I stop the recording, and if anybody's camera shy, they can also take a shot after we cancel it. So I'm going to